Welcome back to the deep dive. Today we're diving into something that honestly changes how we picture space itself.
That's right. For so long, we imagined the space between stars as this, vast empty void.
Just cold, dark nothingness. But it turns out that picture was totally wrong. Space is actually, well, it's busy.
It's teeming with traffic, really. That old view started to crumble back in 2017.
Ah, yes. With the arrival of a very mysterious visitor.
Exactly, Oumuamua. That single object kind of opened the floodgates, didn't it? It showed us we're not in some quiet cosmic cul-de-sac.
We're swimming in what some sources are calling an interstellar deluge.
Absolutely. It reveals our solar system is just one small part of this huge dynamic galactic ecosystem.
Oumuamua was that first tangible piece of evidence, like the first postcard from deep space. But our mission today goes way beyond just that one object.
Definitely. We need to unpack the numbers, the theory behind it all.
Yeah, the startling cosmic math, the other visitors that came after, the incredible new data from the James Webb Space Telescope.
And why astronomers are now, frankly, scrambling to figure out how to catch the next one.
Before it just zips right past us. Okay, so where do we start? The theory.
I think we have to. We need to understand why scientists sort of knew these things had to be out there, even decades before we actually saw one.
Right, they were predicted but never observed, like theoretical ghosts wandering the galaxy.
Pretty much. Invisible ghosts. The predictions came from understanding how planetary systems form and evolve.
Okay, so walk us through that. How does a star system end up, well, ejecting stuff?
It often happens early on. You get these massive planets, maybe gas giants like Jupiter, forming and then migrating inwards, closer to their star.
Okay.
As they move, their gravity is immense. They act like cosmic billiard balls.
Ah, scattering the smaller stuff.
Exactly. They gravitationally scatter countless smaller bodies, asteroids, comets, even entire planets right out of the system and into interstellar space.
Wow. And this isn't just a rare occurrence.
Not at all. This leads to the staggering math. The scale is just mind-boggling.
Give us the numbers.
Well, computer simulations suggest that, on average, a typical star system ejects about 3.5 planets, actual planets, not just small rocks, every billion years.
3.5 planets per billion years, per star system.
That's the average, yeah. Now, multiply that by the estimated 200 billion or so stars just in our Milky Way galaxy.
Okay, my head hurts already. What does that add up to? How many of these ejected worlds are out there?
The final tally is just astonishing. Even conservative estimates put the number of rogue, unbound planets in the Milky Way somewhere between 100 billion and maybe up to 4 trillion.
4 trillion? Wait, are you saying there could be more rogue planets wandering in the dark than planets orbiting stars?
That's precisely the implication. These free-floating rogue planets might actually be the most abundant type of planetary body in the entire galaxy.
That completely flips the script on galactic architecture. We think of solar systems, planets around stars as the main thing.
But the math suggests most planetary mass might be drifting in the dark between the stars. It's a total reframe.
And we've only detected a tiny fraction of these.
Oh, minuscule. Gravitational microlensing surveys have found some, but they've barely scratched the surface of this hidden population. It confirms this ejection and exchange process is constant.
Okay, so the theory was strong, the numbers were huge, but we needed proof. And that arrived in October 2017.
One-eye Oumuamua, the first confirmed interstellar object.
And that naming convention, the eye, that's standard now for interstellar.
That's right. One eye for the first, two eye for the second, and so on. And Oumuamua, one eye was baffling from the moment we saw it. Just deeply weird.
Starting with its shape, right? It wasn't round like an asteroid or fuzzy like a comet.
Not at all. It was incredibly elongated, maybe 10 times longer than it was wide. Some described it like a cigar or a needle, nothing like we'd ever seen originate within our solar system.
And its surface.
Dark and reddish. That suggested it had spent maybe millions or even billions of years traveling between stars, getting zapped by cosmic rays.
Okay, weird shape, weird color. But it didn't act like a comet either.
No, and that was crucial. It showed complete lack of cometary activity. No tail, no gas cloud, no outgassing that we could detect. This suggested it was likely rocky, or at least had a very processed, maybe inactive surface.
But the real mystery, the thing that sparked so much debate, was the acceleration, wasn't it?
Ah, yes, the acceleration puzzle. As Oumuamua was leaving our solar system, heading back out into the void, astronomers noticed it sped up slightly. Just a tiny push.
A push that the sun's gravity alone couldn't explain.
Exactly. Something else was giving it a nudge. And because it didn't look like a comet, the usual explanation, melting ice creating jets of gas, didn't seem to fit.
So what was causing it? It took quite a while to land on an explanation, right? About 6 years.
It did. The challenge was ruling out every known natural cause. People proposed all sorts of things. The breakthrough came with research published in 2023.
What was the idea?
Molecular hydrogen, trapped inside the object.
Hydrogen gas. How would that work? How does a rock store gas like that?
Well, the theory is pretty elegant, actually. During its incredibly long journey through interstellar space, cosmic rays would have constantly bombarded it.
Okay.
This bombardment could have driven chemical reactions inside, creating molecular hydrogen, H2, that then got trapped within the object's structure, maybe in water ice pockets.
So it's like building up pressure internally over millions of years.
Kind of.
Yeah.
Then, when Oumuamua swung close to our sun and warmed up just a little bit,
The trapped hydrogen started to leak out.
precisely, a very slow, very faint release of this hydrogen gas. Not enough to create a visible comet tail,
Yeah.
but just enough to provide that tiny, non-gravitational push they measured.
Wow. So its interstellar journey fundamentally changed its chemistry to give it that weird acceleration.
It seems plausible. It was chemically unique because of its journey, a really fascinating solution.
Okay, so Oumuamua was the mystery, the oddball. But then things got maybe a little more familiar.
Yes, thankfully. In 2019, along came 2I Borisov, and it was basically the anti-Oumuamua.
Sounds-
Borisov looked and acted exactly like a comet from our own outer solar system. It had a big, beautiful tail, a visible coma of gas and dust.
So textbook comet behavior.
Absolutely. And when we looked at its light with spectrographs, we saw familiar molecules, lots of water vapor, carbon monoxide, stuff we see in our own comets.
What did that tell us?
It suggested that some interstellar objects are, pretty normal. They carry the pristine chemistry of whatever distant star system they came from. Borisov gave us a direct sample of the building blocks from somewhere else.
Okay, so we have 1I, the rocky mystery, and 2I, the icy familiar comet. That feels like a nice contrast. But then the story sped up again.
Dramatically. In July 2025, astronomers spotted 3I Atlas, and this one was the real game changer.
Why? What made 3I Atlas so different?
Well, first off, it was incredibly bright, just blazed onto the scene. And it broke records right away.
Records for what?
Speed and trajectory, mainly. It was clocked moving at roughly 137,000 miles per hour relative to the sun.
137,000 miles per hour. That's almost incomprehensible speed.
It's blisteringly fast. And its path through the solar system was the most hyperbolic ever measured. An orbital eccentricity of 6.1.
What does eccentricity mean in this context?
Basically how stretched out its orbit is. An eccentricity greater than 1 means it's not bound to the sun, it's just passing through. An eccentricity of 6.1 is just screaming, I am not from around here. Definitive proof of its interstellar origin.
And it was big, too. You said it was bright.
Oh yeah, orders of magnitude larger than Oumuamua seemed to be. And because it was bigger and brighter, it stayed visible for longer, even at huge distances.
Which gave us a better chance to study it.
A much better chance. And that's where the James Webb Space Telescope came in. In August 2025, JWST turned its incredible infrared eye towards 3I Atlas.
The first time Webb studied an interstellar object, right? What did it find?
It gave us our first detailed infrared look at the chemistry of one of these visitors. And it found something quite unusual.
Which was?
A surprisingly high ratio of carbon dioxide, CO2, compared to water vapor, H2O, and the gas coming off it.
Why is that significant?
Because the ratio of different ices, like CO2 and water, tells you something about where and how the object formed. This unusual chemistry gives us clues about the conditions around its home star, billions of years ago. It's like reading an alien geological record.
Fascinating. And was it very active? Like Borisov?
Extremely active. Researchers used some pretty vivid language. They described it as losing water like a fire hose on full blast.
Wow, so it was really shedding material as it got closer to the sun.
Dramatically so. After potentially billions of years, the deep freeze of interstellar space, encountering our sun's warmth caused this intense outgassing, these rapid transformations.
Did Webb see anything else important, maybe related to, life?
Well, it detected strong ultraviolet emissions indicating hydroxyl gas in its coma. Hydroxyl is what you get when water molecules break apart.
So confirmation of water, but also...
It demonstrates that the fundamental chemical building blocks of life water, carbon compounds, aren't unique to our solar system. They exist out there around other stars, and these objects can transport them across the galaxy. It's a little hint towards astrobiology.
And we got even more data on 3I Atlas, didn't we? From Mars.
That's right. Because it was so big and bright and its path was well predicted, Mars orbiters actually captured detailed images when it made a relatively close pass by the red planet in October 2025. Data we could never get from Earth.
So if we put all three visitors together, Oumuamua, Borisov, and ATLS, what's the picture that emerges?
It's a picture of incredible diversity. Each one tells a different story.
Okay, lay it out.
Oumuamua looks rocky, maybe from the inner part of its home system, perhaps even a fragment blasted off a larger planet. Experienced that weird hydrogen outgassing.
The mystery.
2 Borisov, clearly an icy comet, probably from the cold outer regions of its system, much like our own Kuiper Belt objects, carried familiar chemistry.
The familiar one.
And 3 Atlas, enormous, intensely active, with that unusual CO2-rich chemistry. Maybe a different kind of outer system object, or a fragment of something much larger, formed under different conditions.
The game changer. So 3 very different cosmic postcards. It makes you wonder how many are actually flying through. If we only spotted 3 in, 8 years? Maybe they're still pretty rare.
But that's likely an observational bias. NASA actually estimates that objects similar in size to Oumuamua probably pass through the inner solar system inside Earth's orbit about once per year.
Once a year. So why haven't we seen dozens?
Because most are small, faint, and moving incredibly fast. Our current telescopes, even the big survey ones, just aren't designed to pick up most of them. They slip through the net undetected.
We're mostly seeing the exceptions, the really big or bright ones, or the ones that happen to pass close by.
Exactly. We're still in the reactive phase. We spot them after they're already well inside the system, often when they're already on their way out.
Okay, so knowing they're common and knowing how fast they can move, like 137,000 miles per hour for ATLS, that creates a real sense of urgency, doesn't it? Both for science and, maybe, safety.
Absolutely. It's a huge driver for future observation strategies and even mission concepts. It's partly a planetary defense issue. These things come in fast on unpredictable paths, but it's also this incredible scientific opportunity.
A chance to study material from another star system up close. So what's coming that will help us find more?
The big one everyone is waiting for is the Vera C. Rubin Observatory.
Right. Under construction in Chile? How will that change the game?
Rubin is designed to survey the entire visible sky every few nights, going much deeper and faster than previous surveys. It's expected to be a revolution for detecting transient events, including IOs.
So instead of maybe one detection every few years, what are the predictions for Rubin?
The estimates are somewhere between 1 and 2 interstellar objects per year, maybe 15 or more over its initial 10-year survey.
That's a significant jump, and crucially, it could spot them earlier.
That's the key. Rubin should provide much earlier warnings, potentially weeks or even months before an IO makes its closest approach. That gives us time to react, to potentially plan follow-up observations, maybe even an intercept mission.
Okay, intercepting something moving at those speeds sounds challenging.
Extremely challenging. It's pushing the boundaries of rocketry and navigation.
Yeah.
But the idea is no longer science fiction.
What kinds of missions are being considered?
There are a few concepts floating around. The Southwest Research Institute, or SHIRII, proposed maybe retrofitting existing spacecraft designs for a rapid launch, high-speed flyby.
Using current tech, but adapting it.
Sort of. Then there's the European Space Agency's Comet Interceptor mission. It's already built and waiting in space for a suitable target, likely a long-period comet from our own Oort cloud.
Could it be redirected to an IO if Rubin finds one early enough?
Potentially, yes, if the trajectory and timing work out. But beyond that, people are envisioning more ambitious, dedicated Sentinel missions.
What would those look like?
Like spacecraft specifically designed and maybe pre-positioned in orbit, ready for rapid deployment. Basically, an interceptor waiting for the call.
The speed is still the biggest hurdle, though, matching speeds with something going that fast.
It's immense. The energy required is enormous. You probably wouldn't match speeds entirely, more likely a very fast flyby, grabbing data and maybe even samples on the way past. But the scientific prize, pristine material from another star is just huge.
And we've talked about rocky objects, icy comets, but are there other, even weirder possibilities for what these IOs could be?
Oh, absolutely. The theoretical zoo is quite diverse. Some models predict things like dark comets.
Dark comets, like Oumuamua, but even stealthier.
Yeah, objects that accelerate due to outgassing, like the hydrogen idea for Oumuamua, but without any visible coma or tail at all, even harder to explain.
And that ties into SETI, the search for extraterrestrial intelligence, doesn't it?
There's a connection. A paper came out in 2025 suggesting that any object showing significant rapid acceleration that can't be explained by gravity or visible cometary activity should automatically become a high-priority target for observation.
Not saying it's aliens, but saying it's an anomaly we need to understand.
Exactly. The assumption is it's almost certainly a natural phenomenon we don't understand yet, but you have to check those anomalies carefully.
Are there even more exotic theoretical possibilities?
Well, some models haven't ruled out things like primordial black holes, left over from the Big Bang, potentially whizzing through the solar system. They'd be essentially invisible except for their gravitational influence. Very hard to detect, though.
Okay, so we have the science, the future missions, the exotic ideas. What are the broader implications here? You mentioned planetary defense.
That's a big one. These IOs represent a hazard category we weren't really thinking of before 2017. They come in much faster than typical asteroids from within our system, and their paths are inherently unpredictable until we spot them. We need tracking systems capable of handling the data flood Rubin will provide.
But beyond the hazard, there's something more profound, isn't there? This idea of connection.
Absolutely. For me, that's the most mind-bending part. We're realizing that star systems aren't isolated islands. They're constantly exchanging material.
The stuff we're seeing now, like 3I Atlas, was formed billions of years ago, hundreds or thousands of light years away, around a completely different star.
And now it's here, in our backyard, close enough for JWST to study its chemistry. We are literally analyzing matter from another solar system. It's incredible.
We're just at the start of this, aren't we? The first few postcards have arrived, but the mailbag is probably huge.
We're truly in chapter 1 of a much bigger story. We finally have the technology to start reading these messages from distant stars.
And it connects back to us, to you listening. That philosophical leap is amazing.
It is. Think about it. Over the billions of years the Milky Way has existed, countless collisions, ejections, migrations, trillions upon trillions of objects exchanged between stars.
So material gets spread everywhere.
Everywhere. It means some of the very atoms that make up our planet, make up the oceans, make up, well, you, might have originated around a completely different star long ago.
Blasted out in some ancient planetary collision, drifted through the void for eons, and eventually got swept up when our own solar system was forming.
It's entirely possible. We're part of this vast galactic ecosystem, constantly sharing material. Oumuamua wasn't just a visitor. It was the first recognized postcard from the infinite.
A reminder that we're connected to the cosmos in ways we're only just beginning to grasp.
So the question becomes, what mysteries about those distant star systems, about planet formation, about chemistry elsewhere, are you most eager to see solved as we study more of these cosmic messengers?
That's the question driving this new era. We'll leave you with that thought as we close out this deep dive. Hopefully, when you look up now, you won't just see empty space, but a dynamic, crowded highway connecting